This is the video for section 2.7 in AP Calculus. It is related rates. It is the first video. There will probably be one more in this section. So here we go. All right, this says in the real world, variables often change with respect to time. How fast is something, the area can be changing with respect to time. It could be changing, that would be, square feet per second, or the unit of volume. How fast is the volume of something changing? Cubic centimeters per minute. Or the length. How fast am I running? Could be meters per second. Like whatever the unit is, it's often in the real world has to do with time. It's something per unit of time. So what we're able to do here is we're going to use implicit differentiation to take derivatives of functions with respect to time. Now, what that means is we're going to have this is going to look weird. We're going to have functions that aren't going to have the variable t in them, like the function won't have a t in it. And we're going to take it with respect to time, like dx dt and dy dt, like what used to be dy dx. Y was a function of x. We were taking derivatives of function with respect to x. Now we're taking derivatives of function with respect to time. And since the variable t will not be in our equations, every variable needs the d whatever dt at the end. Whereas before, when we used implicit differentiation, and if we were taking the derivative of a term with just x's, it was just plain old derivatives, and the ones with y's needed that extra dy dt. I'm sorry, dy dx. Now every variable needs a d whatever dt because we're taking these with respect to time. So here's how these are going to look. And today's examples do not have context to them. They're just equations, but the process is worth learning in this video. It's take the derivative with respect to time, and then plug in some given information and solve for something. Starting with the next video, the problems will have lots of real world situation where there'll be actual formulas with areas or volumes or distances. But now it's just x and y. So it says this. Here's our first example. It says let x and y both be differentiable functions of t, and let y equals x squared plus 3. Fairly straightforward equation. Y equals x squared plus 3. Now, here's the way these will look as far as what the question will ask. It'll say find dy dt when x equals 1 at a particular value of x, given that dx dt equals 2. So you'll notice that there's two variables here, x's and y's. And since we're going to take the derivative with respect to time, our derivative is going to end up with both dx dt and dy dt in it. So you'll notice the question will ask for one of those rates. This one happens to ask for dy dt. And it's going to have to give you the other rate. It says given that dx dt equals 2. So let's take the derivative of this, and then we'll substitute in the given information and solve for the missing rate. So on the next slide, so y equals x squared plus 3. So I will write that. Y equals x squared plus 3. We're taking the derivative of this with respect to time. So the derivative of y with respect to time is just dy dt. Equals, now the derivative of x squared is 2x, but because x is no longer the variable we're taking derivatives with respect to, there's a dx dt here as well. That's what I mean when I say every variable has the d whatever dt attached to it. And now we should be able to, there will be a couple of cases in the next video where something doesn't quite fit. We'll worry about that later. For now, we should be able to plug stuff in and solve what we're looking for. This one said, given dx dt is 2, so this is 2 times something, dx dt, there's the 2. It just said dx dt was 2. And it also said when x equals 1. So we're given a value for x. So I plug a 1 there. And now I just evaluate that. Like, let's just figure out that equals. So dy dt, I'll finish it up here. That's just 2 times 1 times 2, which is just 4. So the concept is pretty straightforward. You're taking the derivative of an equation with respect to time. And every variable has the d whatever dt attached to it because none of them will be time. And then you're going to substitute in given information and try and solve for whatever it is that they're asking for. Please pay close attention to what they're asking for because they might be asking for dy dt and they might be asking for dx dt. And in the next video, once we start doing equations with area or volume or surface area or length, like, any of those could be the d whatever dt we're looking for. Okay, I have two more examples, and one of them shows something a little bit tricky, but only a little bit. All right, very similar. It says y equals square root of x. Find dx dt when x equals 25, given dy dt equals 2. Well, first, I'll do what you would do, which is rewrite this equation as y equals x to the 1/2. Okay, now let's take the derivative of that with respect to time. So the derivative of y with respect to time is dy dt. And the derivative of x with respect to t is 1/2 x to the negative 1/2 times dx dt. Like I said, there we go again. We did it every time. Now we have a number to, let's see, x is 25. That goes there. And dy dt equals 2. That goes there. And we're solving for dx dt. So here we are solving for dx dt. So that's what we're trying to solve for. Now just, again, carefully plug the right thing into the right spot. Now, having said all that, could I maybe rewrite this derivative a little simpler? I probably could, and I probably would. So I will, before I start substituting in, I will write this as, that's a y, sorry, dy dt. That is what, 1/2 root x times dx dt. Now I'll substitute in. So dy dt I know is 2. And that is 1/2, that's an over, the square root of x, and I have a number for x, that's 25. And then for dx dt is what I'm trying to find. So I'll leave that dx dt. All right. Now it's just solving this for dx dt. So that becomes, I'll just go to all purple here for no particular reason. That becomes 2 equals 1/2 times 5 dx dt. And I'll finish up here. I have 2 equals 1/10 dx dt. Multiply both sides by 10, you get 20 equals dx dt. Again, we're taking derivatives of function with respect to time, and then we're substituting information and solving for a particular rate. In this case, we were solving for dx dt. The reason why we do problems like this will make a whole lot more sense in the next video. We start putting some context to it, but this is just getting kind of getting the structure of the process. Okay, one more example. That's all I've got. And this says xy equals 4. And it says find dy dt when x equals 8, given dx dt equals 10. So I'm taking the derivative of xy equals 4 with respect to time. This is, in fact, a product, so I better product rule that. So the product rule is the first times the derivative of the second. The derivative of y is dy dt plus the second, which is y, times the derivative of the first, which is dx dt, equals the derivative of 4 is 0. Now, something small, weird happens here. We're going to notice it and then handle it properly. I'm going to start substituting some stuff in here. X equals 8. That's going to go in there. Dx dt is 10. That goes in. Oh, I think I could have changed color. That goes there. Dy dt is what I'm trying to find. That's that. You'll notice I have a variable here. I have a variable here, in particular y. I meant to change color, particular y, but I don't appear to have a number for. So we have an equation here. We may have to go back and figure that out. So it says x when x equals 8. So if I do 8y equals 4, like I may have to go back in the original equation or an original equation to find a particular number. I took the original equation, which was xy equals 4, and I know x equals 8. I plugged it in, so I divide by 8. I get y equals, what's that, 1/2? 1/2. So that's now going to be 1/2. So that's just a little tricky on how to substitute it in correctly. Now let's start plugging stuff in. So x is 8. dy dt is what this problem is looking for. And then plus y, which we figured out is 1/2, plus, I'm not sorry, not plus, times dx dt, which the problem told me was 10, equals 0. Now let's just solve this. This is 8 dy dt. I might do 2 steps at once here. 1/2 of 10 is 5, and I subtract that. I get equals -5. And I divide both sides by 8. I get dy dt equals -5/8. So there, we did 3 examples. They're all similar, and your assignment today is only that. It is only 4 problems. Each of them have 2 parts, so really it's 8 problems. But it's just getting used to taking derivatives of function with respect to time, and then substituting in some values to find other values. So, having said all of that, your assignment is on page 194, and it is just numbers 1 through 4. And each one has an A and a B. And it really just they have the same equation, but different stuff to substitute in. So that is it. Like I said, much longer video to follow tomorrow because there's dozens of different contexts I'd like you to be exposed to. We'll do at least several of them in the next one. So that's it. If I don't give you another video, have a great Monday.